last time. And I'm going to zoom up before you ask, but we don't have much longer in this class together, eh? We're almost done. We'll be teaching to us. I have no idea who's teaching to. Well, actually, I do, but I don't know. So, remember, you are one of the best I want the E and M. That's what I want.
Good point. We're the other guy, but no one showed up.
Yes. Okay, so remember, this is what we started with. We started to ask, we had this eigenvalue, eigenfunction problem. I know I didn't.
No, I didn't.
Okay, that's fine.
He's trying to rewrite it.
That's a huge tablet. I've got like tablet envy. It's a computer, but you can write on it. What won't they think of that? That's crazy. When I started grad school, we had the best computer in our department, in our lab, and it was like a 286 with a coprocessor and a 20 meg hard drive, and both kinds of floppies. This was the best in the whole physics department. What's that?
Did it do anything that just add a lot of big numbers?
No, we used to write programs to like analyze data and talk to instruments. We had to program in actual, like real languages then. Like Fortran. What 477? Actually, we programmed in. Anyways, so we wrote this last time, and we wanted to know what kind of function we could represent like this, and we did say in the end, it would be odd functions, and we talked about odd functions and what they are, so I don't have to do that again. So now, what I want to do is figure out what kind of functions I can represent like this. Well, the way to do this, that's not very good. The way to do this is to just see if I can solve for these coefficients an, and maybe that'll tell me about the kind of functions I can represent. Because I've written something down, but it's not obvious that crazy, this should work for any function. So let's just do this. Now what I want to do to isolate an, I want to multiply both sides by another function, sine m pi x over L. So it's the same kind of eigenfunction, it's just a different eigenfunction. Okay, and integrate between minus L and L. That's what I'm going to do. So that means on the left side of the equation, I have the integral minus L to L f of x sine m pi x over L. And on the other side of the equation, I have the sum n equals 1 to infinity a n sine n pi x over L sine m pi x over L. And then I better integrate minus L to L dx. I can move the integrand or the integration in and out of this series. It's not a problem. If you're more mathy, maybe you're worried it's a problem, and then that sucks to be you. For me, it's not a problem. I don't mind that. And that should be a problem for you. So, well, how are we going to do this? Well, I'm going to look at this thing here. And I'm going to say, well, wait a minute. I know one of these double angle identities. The double angle identity I know is that this is 1/2 times cosine of n minus m pi x over L. It's a double angle identity. Oh, I already said that. Minus cosine n plus m pi x over L. So that means what I really need to be solving here, this is 1/2, then this thing here, sorry, becomes 1/2 the integral between minus L and L times cosine n minus m pi x over L minus 1/2 the integral minus L to L cosine n plus m pi x over L. Okay, let's just do this integration. Well, that means this is 1/2, and then it says, what's the integral of cosine? Oh, that's sine, so that's going to be easy. And then it's going to be L over n minus m pi times sine n minus m pi x over L, L minus L, minus 1/2. And then it's the same thing, but it's got n plus m, so it's L over n plus m pi sine n plus m pi x over L, evaluated at L minus L. Okay. So this last term here, this is pretty easy because I can evaluate this at L and I get sine m plus m pi. Now n and m are integers, right? So sine of any integer times pi is what? Say 0 as if you knew it.
0.
0, that's excellent. Now, sine's an odd function. So what's the sine of the same thing but with a negative argument?
0.
Negative 0, sure. It is negative 0, it's 0, yes?
Sorry, how do we know that m is an integer?
Because in order to satisfy our boundary conditions that we had to have, remember the boundary condition in this case was that y of 0 equals 0, y of L equals 0, and so in order for that to be true, our eigenvalues had to be n squared pi squared over L squared, or n squared pi squared over L squared, right? So that it ends up being sine m pi x over L, which is 0 at the boundary. We made our functions behave that way on purpose.
Okay, thank you.
Yeah?
Do you mind zooming in on the paper?
Doing what on?
Zooming in on the paper.
Oh, zooming in on the paper.
You zoom out.
Thank you.
So did at least give you a good pizza? Is that what that's for?
It was actually not bad.
It
Not
was
bad.
decent.
It was free.
Yes.
And that's the most important thing. Do any of you have that app where you can go around and find out where there's free food on campus?
What?
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 So you've never heard of this? I'll tell you about it. I don't actually know what it's called, but I know that it works because every time we have an event and there's food, at the end of the event, all these undergrads come from everywhere to get the free food. So there is some app, I don't know, maybe it's for everything, you just type in your university, but it tells you where there's events that are giving away free food and when they are, so that you can go later. And then you can eat like this and never have to buy any food.
Trying to. I mean, maybe people are just getting a hold of social media.
I had 2 kids go to Waterloo and they used this thing, so maybe they just made it up and they were teasing me, but I've noticed now it happens a lot more. We had a grad thing at the beginning of the year, at the end of it, all these undergrads just came from everywhere that weren't physics students, and they're like eating all the food. So, anyways, find out about it, let me know. Yeah. Okay, so this now is,
I
think so.
this thing here is equal to what? Oh, we already said that. This is 0. And I'm not going to write 0 with an exclamation mark, emphasis, because then somebody always says, oh, is that 1? Ha ha ha. And I think that joke's getting old.
The paper shake joke.
What's that?
The paper shake joke.
Oh, that's never getting old.
Timeless classic.
It's a timeless classic, that's right. Can you move up?
Whenever we ask him to move the page.
Yeah, with 6 kids, I'm really good at the dad jokes. They're horrible, but. What about this one here?
That's also 0, isn't it?
It's kind of 0.
Everything. What does that mean?
It's kind of 0.
Oh.
But,
Yeah.
but why am I saying it's kind of 0? Yeah.
What if n equals m?
Yeah, what if n equals m? If n equals m, this is actually a bit of a mess, right?
Oh. It's 0 divided by 0.
That's the most 0 you can be.
N minus m. Like this is 0, sorry, this is 0 except for the case n is equal to m. When n is equal to m, now it becomes a bit of a mess. Before that it didn't matter, and this one here it doesn't matter, n can be m, who cares? But now if I take n divided by m, or n minus m is 0, it's a bit.
Oh, that part, my bad. I'm not saying that part.
Yeah, okay. Now, of course, you could look at that. You could look at that and say, oh, but if I do a Taylor expansion, everyone loves Taylor expansions?
Yeah.
No.
Right.
Of course.
If you do the Taylor expansion of that, the first term is just the arguments of sine, so it's going to be n minus m pi x over L. So then you can actually see that it works out fine. But typically what we do is instead, we'll just work that out separately. So this is 0 if n is not equal to m. Okay, and now let's look at the case n equals m separately. Oh look, anyone want a mask? Oh, there's like some cool masks here.
They're uncomfortable.
Are they uncomfortable?
Yeah.
So if n equals m, if n equals m, then what we have is our first term looks like this. Well, actually, what we can do is we can just evaluate the whole thing if n equals m. We can just start over and say then, if n equals m, the integral minus L to L of sine n pi x over L times sine n pi x over L dx. So now I've set in n equals m. So this is the integral minus L to L of sine n pi x L over 2 squared, which is the integral of, what is it? It's 1/2. What is sine n pi x over L is 1/2. Is it 1/2? Yeah. Is 1/2 the integral of 1 minus cos 2 n pi x over L. I think that's right. It's another double angle identity. Now, this thing here is just 0 again. When you integrate this term, it's going to be 0 again. Okay? Which means that this whole thing is 1/2 times the integral minus L to L dx, which is just 2L over 2, which is L. So the way we often write this L. This is another delta. So maybe that's not a very good look. It's a Kronecker delta, we call it. And it's similar to the delta function that we saw, except it's just something that we use for indices. So this is, m and n are integers, And if m is not equal to n, delta is 0, and if m is equal to n, delta is 1. It's just a common. So now what we could do is we could go back. Why, let's think about why the heck we were doing this again. We were doing this to get this, right? Yes? See ahead.
Why does cos go to 0 if it's an even function?
Well, it's like this. Like here's cosine. Okay? If I take the cosine between here and here, right, I'm getting just as much positive as negative, and so they cancel out. Sorry. Right, this is my cosine function. So I'm doing it, it's symmetric here. It's just as much negative as positive, so this answer is going to be 0. Okay, so now that means what I can do is I can say, I'm going to use this, I'm going to put it back, don't worry, that the integral minus L to L of f of x sine m pi x over L equals the sum n equals 1 to infinity times a n times L times delta mn. So all we've done there is multiplied it by this sine n pi x over L, this other eigenfunction. We integrate over minus L to L, and this is what we get on the right side. So all of the terms die except the term where m equals n. And actually what that allows us to do, okay, is it allows us to just write am equals 1 over L, the integral minus L to L, f of x sine m pi x over L dx. So now I have an expression for that coefficient, for any function f. Any function f which is odd, otherwise I'm not going to be able to do this. This is a m. Yeah. Now it doesn't matter, I could say n and then I just have to change the n here. Because remember what we did is I had sine n pi x over L. I multiplied them all by another function sine m pi x over L and then integrated. On the right side in the series I have this delta nm, and that means I only care about n equals m. So then all the n's turn into m at that point. So now this works for odd functions on minus L less than x less than L. And I can represent any function like that. I can also write this another way. Okay? So let's imagine we're writing. Did I move that too far? Yeah. Do you still need that? Yeah, okay. Some do, some don't. I'll be slow, I'll let you write it down. Yeah. What's that? Yeah, there you go.
Okay, wait.
Sorry, yes?
I'm still confused about how you said that it's going to be 0. I believe you, absolutely. But I mean, just like with an even function, like I don't see that. I understand with an odd function, if you're integrating from like negative L to L, it'll cancel out first. But if you have an even
Well,
function,
here's a cosine function here. So, like this is cosine of x, right?
yeah.
So now I'm going to integrate it over one period.
So it's specifically because we're integrating over one period.
Yeah.
Okay, then I.
Well, and because here it's more than one period, well, yeah, because I have that 2n pi. So 2 pi is one period,
Yeah.
and so it's good because of that, it's at least multiples of a period.
Okay, then that makes sense. Got it.
Okay.
No,
Yeah, well, okay, so it's true that, so it's true that even functions, you know, I can say, okay, so here's, yeah. So with an even function, you could say the integral minus L to L is 2 times the integral 0 to L, which is what we're going to do now. But if I did that, all I'm doing then is looking at, I'm trying to answer your question. I'm trying to look, all I'm doing is instead of doing this whole thing, I'm saying, oh, because it's even, I can just look at this bit, but this bit still integrates to 0. Odd functions with symmetric integrands will always integrate to 0, but even functions can still integrate to 0 if they're positive and negative, so that the negative parts exactly cancel the positive parts. It's just that odd functions do it all the time. Yes?
Are we solving for AM or AN?
Okay, so what we did, let me just recap here. So we started here. We started here. And we said there's a sum and all the things are n. What I want to do is I want to isolate for it. And so I multiply it by a different eigenfunction, sine m pi x over L. It's a different eigenfunction. Okay? So now on the left side, it's sine m pi x over L. And on the right side, I have both n's and m's. Okay? What I do then, or after, you know, some algebra, we do a thing and we get this relationship here, which has m's and n's, on this side, again, just like it did before, and on this side it only has m's. Okay? But this thing here is 1 if m equals n, and 0 otherwise. So now all of a sudden, there's no point talking about n's that aren't equal to m, because they're 0. So that's why we get this, but now this is why they're m. Doesn't matter, I can also write this as an equals 1 over L, blah, blah, sine n pi x over L. I could write this as p or q or trees or whatever, as long as it's an integer. Yeah?
Do we just make up the sine m pi x over L?
No, what do you mean did I just make it up?
No, like, so like now we have idea of n, if a sub n, if we have sine m pi x over L. But like, where did we get that function?
Okay, so where do we get that from?
I get that it enables us to solve this, but like, if we're given a problem, we just make up a sine m pi x over L.
So when we did this boundary value problem, we said we're going to have eigenfunctions. Sorry. We'll have lambda n in general, which are eigenvalues, and you don't have to write this down because this is just for discussion. And I can have phi n. These are eigenfunctions. And you can't see it?
I'll turn it back.
So the eigenvalues are whatever. They could be, like in this case, they're integer times pi over L. They could be like in the square well potential, finite square well, where they're determined by some transcendental equation. They could be whatever. But there are eigenvalues and then eigenfunctions, each, and they're pairs, right? For each eigenvalue, there's an eigenfunction. What we're trying to do is we are trying to write a function f of x as the sum over lambda n phi n a n phi n of x over eigenfunctions in general. So we did a specific example where these phi's are sine and are sine functions so far. But this is generally true. Also, the thing we did with the sines and cosines to do that integral takes advantage of this, in that eigenfunctions to a Sturm-Liouville problem are all mutually orthogonal. I'm not going to show it. We're not even going to talk about it beyond this general case, because we're just doing Fourier series. But a Fourier series is a specific example of a Sturm-Liouville, or the solutions to a Sturm-Liouville equation, and they all have this orthogonality. So I knew it was the case because it's the solution to a boundary value problem, and I knew I just had to multiply it by another eigenfunction and then integrate it, and they're going to be orthogonal. There is so much interesting and cool stuff that goes on behind this. Like, we're going to do sines and cosines, but there are so many eigenfunctions that you can use. There are things like you could do Legendre functions, which, like I said, show up in hydrogen. You can do Laguerre functions, which show up in hydrogen. You can do Hermite polynomials, which show up in the harmonic oscillator. You can do spherical Bessel functions. I don't know if there's an infinite number, but there's a large number of eigenfunctions that we can use. Okay, so wait, where am I now? I'm there. Okay, I can also write okay, this is an odd function that I'm representing. This is an odd function as well. So altogether, it's an even function. So that means I can write this as, so odd times odd is even. Are we okay with that?
Yes.
Okay. So I can write this as 2 times the integral 0 to L f of x sine n pi x over L dx. So that means I can write, if we want to, another way. I can write them like, oh, sorry. Why did I do that? It's because I'm an idiot. At least we know that now. So I can write it like this, or I can write it like this. It's the same thing. And a lot of times what we might do, let's do an example to show this. Let's do an example.
Wait, go back.
Okay, and let's suppose I have
Go back.
pull it back up. A bit more. A bit more.
Go back more.
Perfect.
Why are you laughing? Go back.
I should invest in what? I have a tablet. I have an iPad.
You should use it.
It's pretty old school.
So, question.
Yes.
In your school of old, were there nice projectors on the screen?
No, we used to have overhead overhead transparencies and overhead transparency pads.
I don't, what's the word, follow. I have no clue on.
I did that.
Oh,
You know what that is. Okay, thank you. You were making me feel really old. And as a matter of fact, when we used to go to conferences and give talks, we would have written on overhead transparencies and then like photocopy things onto transparencies, and you'd go to the place to give a talk, and we'd have our talk in just all these overhead transparencies, and you could never change it, and you couldn't work on your talk while you were part of the audience 5 minutes before your talk. So technology has enabled us to be really lazy. But anyways, okay, so I want to do an example. Yeah, you could write on the transparency. Yes? No? You're just scratching your head? Okay. So I want to look at this first as f of x equals x between 0 and x, between 0 and L. And the reason I want to do it between 0 and L is because I'm going to do this right now. I'm going to do an odd extension of the function, make it into an odd function, and then I'm going to find the sine series for the odd function. And then later, when we do cosine series, which are obviously for even functions, I'm going to make an even extension of the same function and get a cosine expansion, which is then another way of representing exactly the same function. Okay? So that's the reason why I'm looking at f of x 0 less than x less than L, and I want to extend to minus L less than x less than L. So what I care about is, say, this function here, f of x, and I'm going to make it into L minus L. So in between 0 and L, it's the same function. But the series representation I'm going to get also extends that function into this regime here for x less than 0 down to minus L. Now, it turns out, though, this function is going to be periodic. What we're actually doing, okay, is we're actually finding the this is what we're actually finding the series solution of. Because sines and cosines are, what do we call it, periodic, anything we get out of it is also going to be periodic. And here's something that's interesting about this. Well, okay, let me ask you, let me give you the opportunity to be brilliant. I love giving these opportunities. Does anything strike you as weird? I'm going to write this, I'm going to use that kind of series expansion. I'm going to make this out of sine waves, and I'm going to get a function which looks like this. Can you see anything bothersome about that? Yeah?
Sine is continuous and this little jump.
Okay, that's true. And that actually will cause us trouble. Sine waves and cosine waves have trouble with discontinuities. Does anyone know what we call that? It's called Gibbs phenomenon. That sine and cosines. So they always actually have little wiggles at the end. And as a matter of fact, have you ever seen it when you take a square wave on an oscilloscope? Do you know what an oscilloscope is? Okay. It's got these things at the end. Because you're always making, you know, when you make this, it's basically kind of a physical manifestation of this. And so you always get these wiggles at the end when it jumps up and down. But there's something else about this. Yes, hi.
Hi. Is it because sine waves and cos waves have like a curve, and this is a straight x equals y line?
No, that's a cool thing about it, because it is true. Like the first sine wave is, you know, not going to look like this at all. The second one's going to look a little better. Sorry, yeah.
Maybe is it like because these ones are only ever really increasing except for at a specific point?
No? Yeah?
Does it look like tan? Is that the thing?
No. Okay, so what is the sine? What does that function do right here? Sine n pi x over L for any n. What is it? At x equals L. 0. Sine n pi x over L at any L, for any n is 0 at x equals L, because it's sine n pi. Our function is clearly not 0. As a matter of fact, it's its biggest value. Yeah?
Hi. I heard that, everyone. Is it 0 because it's the biggest value but also the lowest value, so then it takes the average and you get 0?
Right, that's actually true. And so the problem we would have if we were just thinking of this is I can never represent my function properly because sine is 0 here and my function's like L there. So it can't be 0. But if you remember that actually what we're doing is looking at the periodic extension, then actually what it's doing is finding this. And so what's happening is the first time I'm doing this, I'm getting this curved, I can even draw on top of here, right? I'm going to get this, I'll draw it on one of these. The first one's going to go like this. And then the second one's going to have, you know, after I add 2 functions together, it's going to be, I don't know what it's going to be, it'll be like this. And then 3 functions is going to be like this, and 4. And in the end, it's going to get better and better, but it's always going to rush down and go through 0 there at the discontinuity. Yeah?
Isn't like f not defined at L?
It's discontinuous.
Like, but it's also just not defined. Like you're saying it's in this maximum value. Like, where are the open dots is what I'm asking. Like, is that relevant?
Yeah, I mean, there could be an open dot here and a closed dot here or whatever. It's discontinuous, but it has to be defined everywhere. Yeah, but the Fourier series will fail at a discontinuity. So actually, one of the rules about being able to write a Fourier series is there has to be a finite number of discontinuities on a closed interval. So on the open interval, minus v to infinity, I'm fine. But if I take a closed interval, I can only have a finite number of discontinuities. So I could have a little section here where it's not defined. It wouldn't work out. Okay, so now that we've gone through that, okay, so I'm going to say that f of x is equal to x for minus L less than x less than L. This is my odd extension of my function.
Please remember paper.
Yeah, okay.
No, don't. Just keep going.
Thank you.
This is my odd extension of the function. I just change this interval between minus L to be minus L rather than 0. And since x by itself is an odd function, that's automatically the odd extension. Okay. So that means now that my sine series is going to have coefficients which look like this, and I can write them as n or m or any integer I want. I'm going to go back to this. This is integral 0 to L. Why did I write this like this? X sine n by x over L dx. Okay? So now how are we going to integrate this? We're going to integrate by parts. That's a fantastic idea.
No.
What? If you don't know how to integrate by parts, you derive how to integrate by parts right now. You say, oh, I have two functions u and v, and I differentiate them. And so I say that's duv plus v du. And so then what I do is I integrate, du times v, du times v, and u times dv. And then I integrate everything, and that tells me that uv equals the integral of v times du plus the integral of u times dv. And then I say that the integral of v du equals uv minus the integral of u dv. So now I just derived integration by parts just by knowing the product rule. Everybody who fell asleep during entire first year calculus, put up their hand with Daniel. Yeah. Oh my God!
I didn't take first year calc.
We didn't have lectures to fall asleep in. It was all online.
Yeah.
It was even asynchronous.
It was async, and so was the.
No, first
Yeah,
term
no, I'm
counts.
saying
Oh my gosh, I went.
Yeah, when we taught first year during COVID, even though it was asynchronous, we had synchronous components, so it means that we had to have people up like at all hours of the night.
It was kind of unfair. I can't lie. Like even the algebra was asynchronous.
Okay, anyways, now we know how to integrate by parts. And so in this case here, I'm going to say, oh, and now I've screwed my notation up, so I have to just start over. So here I have v du. I'm going to say du is equal to, what should I say? Du is equal to?
X.
Really? Then I'm going to integrate it. I want something that's easy to integrate. Because I want the x to go away, right? So, for instance, you should always be integrating the thing that looks like a sine or a cosine or looks like e to the x. Because those are easy to integrate, and then when I differentiate the polynomial term, it always drops the powers. Okay? So I'm going to say du is sine n pi x over L, and then I'm going to say v is equal to x, and so then u here is equal to L over n pi negative cos n pi x over L, and dv equals dx. Did I get that right?
You gotta switch V and U.
Well, I don't know, because I have different U's and V's here. Well, we forced me to do something different, so I'm doing it as I go along.
Wait.
Wait,
Well,
I think it's right.
isn't DV1?
Oh, so you usually use the other U's and V's too?
Yes.
Like, write X and then the derivative of it, and then the thing, and then
Okay, so now I've got V du, so now I'm going to have to write the integral of x sine n pi x over L dx. So now I'm going to say this is u times v, so this is minus L over n pi times x cos n pi x over L, evaluated at L and 0 there. Minus x L n pi, okay, cos n pi x over L, plus, and now I'm going to have this times this. It's minus, but it's minus minus, so now it's integral 0 to L, L over n pi, cos n pi x over L dx. Let's make sure I got that right. L over n pi, integral 0 to L, cos n pi x over L. Okay.
why is there an X?
So now this is just this integral here. So this thing here is equal to what? What is cos n pi x over
depends on it.
this is going to be equal to minus L squared over n pi cos n pi. Now it's minus minus, so it's plus. Oh, and then 0. Because x at 0 is 0, so that term goes away for us. And now I've got this term here, plus, and now I've got to integrate this, so this is going to be L over n pi squared times sine n pi x over L, evaluated at L and 0. Well, this term's easy. This is 0, right? So this gives us 0. And it's this first term cos n pi plus 0. So what is cos n pi equal to?
-1 or 1, depending on the kind.
Right, so cos n pi let's draw, and I never remember this stuff. You guys who can't remember stuff, I'm with you, I feel you here. So I'm just gonna draw this here, and cosine goes like this. So cosine of 0 is 1. This is cosine of pi over 2, so this is pi. So this is minus 1, and then this is the next one, which is 1. So that means that cosine of n pi equals minus 1 to the n. Which means that this thing here, so the integral here, let's go back, integral x sine n pi x over L. So I've got a minus there, so I'm going to absorb that. I'm going to get L squared over n pi minus 1 to the n plus 1, because there was a minus sign here. So I'm going to absorb that and make it into a plus 1. And remember, what I really want, though, is that recall, an is 2 over L times the integral 0 to L x sine n pi x over L dx. So that means one of these things is going to go away, one of the L's, and I'm going to end up with 2 OL over n pi times minus 1 to the n plus 1. Which means I can write, finally, f of x. I can take the 2 out because 2 doesn't depend on n. I can take the L out, L also doesn't depend on n, and neither does pi. And then I can say I have the sum n equals 1 to infinity, minus 1 to the n plus 1 over n sine n pi x over L. So now we've made our very first Fourier series.
Oh, that's what we're doing.
You are no longer Fourier series virgins. You have now that is not what I'm trying to say at all. I don't know. But now we can write, we took this art, and think of what we just did. We took this function, which is a nice straight line, and we made it out of a bunch of wiggly things. Right? And we took a function which is discontinuous, and we approximated it by a bunch of wiggly things. And by adding more and more high frequencies, that allows us to kind of
Other way around.
get kind of fill in the dots and get closer and closer to these endpoints where the discontinuity is. So like I'll just, again, it looks like this. We know that our first sine wave was going to do like this, and then our second one was probably going to do this, and so on. And then eventually we will get something which looks very much like this, the function we have, and in the limit n goes to infinity, it's exactly the function except that there's one point. This is called a representation of the function. It is, the function exists, it's just like, and I gave this description kind of outside on Monday, but imagine we have a vector. We're all familiar with vectors in Cartesian space, right? Totally familiar with these. So if I have a vector, that vector lives independently of how I write it. I can write it in Cartesian coordinates, I can write it in spherical coordinates, I can write it in polar coordinates, I can make up a coordinate system. The vector doesn't care how I represent it. The vector exists independently of how I write it. All those things are just different ways of writing the vector, different representations. This is the exact same thing, but in a function space. So this is an infinite dimensional Hilbert space. And the functions n pi sine n pi x over L are all the basis functions. And I could represent that function as a point in that space. And don't worry about the fact that the axes are functions or that there are an infinity of them. Don't worry about that. Those are details. But the concept is the same. This is an equally valid way of writing that function. And there are tons of different ways to write this function. Sorry, yeah?
So what you're saying as an infinite sum. It's just just restating what you said. We rewrote x, but something that contains x, and then an infinite number of terms.
Yep.
Okay, got it.
Yep. And it's an equally valid way to write it. And so maybe this particular example is a little bit weird, but a lot of times what you'll want to do is if you have a particular symmetry of your problem, you write any functions in terms of the symmetries of that problem. And so even if you have, say, an initial value, initial function, initial distribution, which doesn't have that symmetry, if I rewrite it in terms of functions that do, all the math becomes easier. Okay? Mostly because the eigenfunctions that you have will all be orthogonal. To be honest, I'm not totally sure when you would use this. Okay, if you were doing quantum mechanics and you were trying to add two angular momenta, you would use this. You would totally use it and it would make sense. But even though, I'm not sure for most of you if you will do that. But adding angular momenta and doing it like this in quantum mechanics is more advanced than you will do next year. And it may be more advanced than you do in fourth year. I don't know. Yes? Sorry? Put it in decimals? What? Oh. Oh, you did it. Cool. Oh, I wish I would have done that. You should get extra marks, but you won't.
For what?
Okay, so now I gotta check the time. I forgot my phone.
2:30.
2:27.
No, it's 2:57.
Oh, so I got tons of time we can talk about. Okay, good. So now, you regret saying it that way, right?
It's 2:47. It's 2:47. If it was, it would be.
What do we do?
But it looks close enough.
What do we do with even functions? Clearly, I'm not going to take an even function and I'm going to represent it as a sine series. Although I could take an even function and do an odd extension of that and somehow do it. Sorry, yeah?
Did you just write anything? Because we're looking at the bottom.
I did write something. It's a secret.
We can keep it that way.
I'm good at keeping secrets.
Yeah.
So what do we do with even functions? Well, we can go through, and I'm not going to do it, but we can go through exactly the analogous procedure with cosines. And so we can say, and you get okay. You have to treat 0 separately because with cosines it's a little bit different, right? The cos of 0 is 0, so it causes us a bit of grief. And now if we do this, we get AN equals 2 over L. Exactly the same process as before. The only thing that's a little bit different when we do the derivation, no, it's the same thing. It's just an odd times an odd function gives us an even function, so we change it from minus L to L, from 0 to L. But if in an even function, then it's an even times an even, which is more trivially even, I think, than odd times odd. So,
What does that say? Go through
now
what percent?
we didn't do any of the steps for this. Sorry, yeah?
Like, kind of have an idea of like what we need to look out for and use versus how this is so like, we need to know how to get from like where we started to like this expression for and.
Like for example, on the exam.
So I would certainly expect you to be able to derive what we just derived with the sines, or with the cosines. Even though we didn't derive it, I'd expect you to be able to do it. Was that? But I also wouldn't, if I wanted you to use it in an exam, I would not expect that you remember it. So if I want you to use it and not derive it, I will give you that relationship. So I will give you this, the Fourier sine and cosine coefficients, the expressions for them, if I want you to use them to calculate a Fourier series. Actually, realistically, I'm probably going to give them to you even if I ask you to derive them, because why not? That's, the answer isn't the way you get the marks for, it's the derivation.
So you're saying we should know how to derive that first Fourier series you showed?
And this one.
I'm showing you should be able to derive these expressions for the coefficients using orthogonality of the eigenfunctions.
Could you Move the paper back down, please. Other.
You still want that?
Yeah.
Okay, so now what I want to do is I want to use this. Use a cosine series representation of so in this case here, it's the same function on 0 to L, but now instead of extending that function oddly, or making an odd extension of the function, let's say it that way, to do the sine series, now I'm going to make an even extension of the function, and now I'm going to generate a cosine series. In the end, they're both, between 0 and L, they're both equally valid representations of the function. Although, like you noted, we could just write x. Somehow it seems easier, doesn't it?
It's just kind of funny. We're writing an infinite number of things that contain x.
To solve x, yeah. Or to say x, yeah. Why? Don't say why. Why are we doing it? Because, well, I could try and I could find Fourier sine and cosine series of much more difficult functions, right? Where maybe it's not as, I don't know, funny. But then it would be really messy math. Sorry, no?
No.
No? Everyone's just stretching? Fourier series allows you to solve boundary value problems. Maybe, okay, we're gonna come to here. I'm gonna write here, because that's where we'll start next Monday. And I want to show you something, which is where you might use this. Now where you might use this is something like this. Okay, you don't have to write this down. Here's a bar of metal.
We don't have to write it down.
Here's a bar of metal. X equals 0 to x equals L. I'm going to say that the temperature at this end is 0. The temperature at this end is 0. Okay? So I take this bar of metal and I hold the two ends at 0. Okay? But of course my initial value isn't 0 everywhere else along the bar. This is solved by something called the heat equation, which is, you talked about it?
No, you mentioned it.
I did? Okay, so I'm going to have a function, say, I'm going to call it psi of xt, d2 psi, dx squared, and now I'm trying to remember how this goes. Oh, and now these actually have to be partial derivatives. I just can't remember if this is plus or minus. Does anyone know the heat equation? Blah, blah, blah. I think if this is right.
No,
I think this is right. For a one-dimensional heat equation. So, the reason these become important, if I want to solve this function, which is the temperature, is a function of both position and time. And this makes sense. If I have a rod, and suppose I take it out of the oven or something, or I heat it up with a torch, whatever. Then I stick it in my device, which holds the two ends at 0. Now I want to see the evolution of temperature over the whole bar as a function of all the possible values of x and all the possible values of time. Yeah? It's positive? Okay.
Also, on this random website that I just found,
Yeah?
it does list the thermal diffusivity constant as c squared. Is there a distinction there?
I just made up a number, but yeah, that's fine. The reason, so now why do we do this? We do this because we can write the temperature function. This is called separation of variables. It's not part of this course, but it's why we do boundary value problems. I write it as two functions, a function of only the spatial variable and a function of only the time variable. And so now I put this in these two equations. I plug in psi like this into these two equations. And this means that I get x double prime t equals 1 over c x t prime. Because on the left side, I'm just differentiating with respect to space, so the t function just hangs around like a constant. And on the right side, I'm differentiating with respect to... Yeah, I'm not sure about that. But anyways, I'm just differentiating with respect to time, so this just hangs around like a constant. So now what I do is I divide both sides by x times t. And I get x double prime over x equals 1 over c t prime over t. So now on one side here, I've got functions, I've got something that only depends on the spatial variables and the spatial function. Here, this only depends on the time and the time function. And they're equal all the time. So how can that be? If I have something which only depends on space, and it's equal to something that only depends on time, and they're always equal, what does that tell us about it? It has to be a constant. Has to be a constant. And so we call that constant, no surprise, lambda squared. So now I get x double prime equals lambda squared x. I'm going to call it, I call it minus lambda squared. Yeah, now it all makes sense. I call it minus lambda squared for reasons that doesn't matter. Okay, and then I get 1 over c t prime over t equals minus lambda squared. And so now, instead of having a partial differential equation, I have two ordinary differential equations. And they are x double prime plus lambda squared x equals 0, and t prime equals minus lambda squared c t. Okay? And so, and I know that if my temperatures at the boundaries have to be 0, that has to show up in the x function. So that means that x of 0 equals 0, x of L equals 0. So this thing here now, we recognize. That's the problem we've been solving. Okay? And the eigenvalues, lambda squared or minus lambda squared, are determined by the eigenvalues that allow us to solve the spatial part of the boundary value problem. And that's why I called it negative lambda squared, because I knew I was going to have it be negative in order to be able to use sine n pi x over L and satisfy the boundary conditions. Now on this side, so this gives me x of x is, some constant a sine n pi x over L. That gives me the eigenvalues and eigenfunctions. And now this tells me here that t is e to the minus lambda squared c times t. So interestingly, I've got minus e to the minus n squared pi squared over L squared c times t. And now these x of x okay, what's missing here is I'm going to have psi of 0 is some function of time. Okay, that psi of 0 being some function of time is what's going to tell us all of the constants in the solution that we need here. Okay, so this is the very, very, very most rapid, roughest introduction to partial differential equations, which is what that is, a differential equation with two independent variables. Separation of variables, which is how you make it into ordinary differential equations, and why then we care about solving this kind of problem. Because the heat equation, all forms of the heat equation will give us something like this. The wave equation will also give us something like this. And the diffusion equation will also give us something like that. Those three equations make up most of physics. Okay, the Schrodinger equation is just a wave equation. Okay, and the real Schrodinger equation looks like, so I gave you what's called the time-independent Schrodinger equation, but I'll still do it in one spatial dimension. Sorry. Schrodinger equation looks just like a heat equation. It's a diffusion equation, but it's a diffusion of probability. So actually that's what's going on in the Schrodinger equation. It's just diffusion of probability. And there's this little I thing, but we're not going to worry about that. Okay, I think this is a fantastic place to stop. One reason is
We have 7 minutes.
I have to give you guys like 15 minutes of class time to do evaluations. That's the rule. So we'll do that on Monday. I mean, the last 15 minutes on Monday, I'll just let you